Hello everyone, welcome back to another lecture in this series. So in the last one, we talked about separation of variables and we did some problems. But today we will talk about another topic which is called as homogeneous equations. So what exactly is homogeneous equation is essentially we need to consider two functions and then we have a derivative associated with that, but we can express it best if we write that down, right? So let's emphasize and let's learn what the homogeneous equation really means. So differential equation of the form, and here we write the form to understand what exactly the situation is. So it's dy by dx, and that is equal to a function that depends on the two variables that we just discussed, x and y. And in the denominator, we have another function phi, which also depends on x and y. So here we see that we have a function, actually we have two functions, and we have a derivative which looks like a gradient, and this actually looks like a gradient, but we will see what exactly it looks like. So the equations which look like this or have a form which resembles this kind of equation is called a homogeneous equation given certain constraints, right? And what are those constraints? So it's called a homogeneous equation. Well, actually, it will be equation, not equations, right? If each term, which means the terms that belong to f of x and y and phi of x and y is of the same degree, It's pretty easy to understand. We have discussed what we exactly mean by degree, and we see that these terms f of x and y and phi of x and y, they should have the terms which share the same degree, essentially. In order to understand this problem better, let's do an example. So let's do an example to demonstrate what homogeneous equation really means. Let's see, we want to find the solution of the differential equation and we make an attempt to write it in a form which is not quite obvious at this point, but then we will rearrange it and we will shortly see that essentially is how homogeneous equations are written, right? So let's say if we have a function 2xy plus x squared, and then we have a dy by dx, and that is equal to 3y squared plus 2xy. So if we rearrange this equation, we see that this part over here is analogous to the definition fxy, and this part over here is analogous to phi of x and y, and that becomes the denominator. So let's rearrange the equation and write it exactly in this form. So we have dy, and this is the solution essentially. You can pause the video at this point and try to solve this problem, but then just for the sake of time, I'll try to do it and show you how these equations are solved. So let's say we have dy by dx, and that is equal to, if we bring the left hand side to the denominator, we have 2xy plus x squared. So this is the form of the homogeneous equation which we discussed, and as you can see, it has the same degree, which means that x is multiplied with y, so the number is 2, y is raised to the power of 2. Again, in the denominator, we have x multiplied with y and x raised to the power of 2. So we see that the degree is consistent, hence we can treat that as a homogeneous example. So just to reiterate on the statement, there are certain conditions when we can say that it is a homogeneous equation, and very importantly, it should be of the same degree. And this is the key idea to solving an equation. As you can see shortly, the techniques that we will use do require this consistency criterion. Okay, so now that we have established this form, let's try to solve it. Okay, so put y is equal to vx and take a derivative of it. So it's very obvious. Let's take a derivative, dy by dx, is equal to, use the chain rule, and we get v plus x dv dx, which means that we are taking a differentiation of v first, keeping x constant, and then x keeping v constant. So this is how we break down this substitution and take a derivative of it. So we can rewrite and substitute. So substitute y equals to vx in equation 1, as we see over here. It's just at the top. So in equation 1, and the following expression is obtained. So what kind of expressions are we expecting? That's something we will see, right? So since we have dy by dx on the left, let's replace it with the substitution we just made and took a derivative of, right? So v plus x dv dx, and that is equal to, very easy to understand, that is 3v square x square plus 2vx square by 2vx square plus x square. So if you reduce the x square from both the numerator and the denominator, we have 3v square plus 2v upon 2v plus 1, right? So we have reduced this expression of v of the initial homogeneous problem into a problem which has v and x and not v and y. Of course, because of the substitution, but we need to play around with it a little bit, okay? Right, so once we have that, let's just try to move forward and solve the problem. So x dv dx from the previous one, we take the v on the left hand side to the right hand side, resulting in this expression 2v by 2v plus 1 minus v. It's very easy to understand. That is equal to v square plus v by 2v plus 1, right? So now we have an expression where we see that there are two values on the left hand side, and we have an expression, a factor on the right hand side. So now what we will do is we will take this expression 2v plus 1 divided by v square plus v, and then we do this substitution, because as you can see, this is equal to this term over here is equal to this term over here. So what we do is we take the term on the right in the denominator and then take x on the right, so that we arrive at this expression. So this expression is something which helps us to solve the problem now, because now we have isolated v and x into a form that can be integrated, and that is the very idea of the substitution which we made in the first place, that can be integrated. The integration part is very essential, otherwise it won't be able to solve the problem for obvious reasons, right? Okay, so now we need to do an integration, and that's very straightforward. So if we integrate x, that's x actually, that is equal to v plus 1 upon v square plus v. We are doing an indefinite integration, not a definite one. If we had done a definite one, then we could have given some limits, but we are expecting a constant at this point, so that's not a problem. We can just go ahead with the indefinite integration, and then we arrive at the conclusion that log v square plus v is equal to log x plus log c. This is a very easy exercise. You can see, like, let's say if you take z is equal to v square plus v, and then if you take dz, that is equal to 2v plus 1. So that essentially, if you do an integration, this expression reduces to integration dz by z, and that's exactly equal to the one that we have over here. So this kind of substitution really helps us in moving forward with our calculations, so that it makes our life simple, right? So then we have v square plus v, and then the other aspects. Now we need to resubstitute back the expression of y. So v square plus v, if we turn off the logs, we see that that is equal to cx, following usual logarithmic property. And then, so I just draw a line over here. This is the results that we are looking for. Now replace back y into the above expression, right? So if you have to replace back y, we see that that is equal to y square plus xy, and that is equal to cx cube. Here we are. That's the answer. So I'll just highlight the answer so that in case you're doing it from the beginning, you can match your answer to the problem. And this is the final answer. You can pause the video, go back and then try to figure out how we solve the problem and then attempt similar problems on your own. Right. So once this is done, we take some time and then move on to the next concept, which is equations that are reducible to the homogeneous form. But then we use a different kind of substitution. We use some kind of an additive substitution. So let's write that down for the moment. So equations reducible to the homogeneous form. Right? So equations reducible to the homogeneous form. This particular problem of this particular topic really involves another kind of view of how you can approach these problems where you have similar kind of variables, similar kind of values associated with the derivatives that we just solved in the last example. So let's write the definition. So equations of the form dy by dx, and that is equal to a small x plus b small y plus small c equals to capital AX plus capital BY plus capital BC. Now, these kind of expressions can be reduced to homogeneous form using the substitutions. So in the last problem, we saw that we solved the problem using a substitution which was rather multiplicative. So just to show you, this was a substitution that we did. But in this problem, however, there is a slight change. And it also gives you an idea how we can approach different kinds of problems which are of the same flavor, right? So using the substitutions, small x is capital X plus h, and y is capital Y plus k, where h and k are constants, right? So we see that this is the substitution that we are doing. And the way it makes our life a little easier is because if we take a derivative of dy by dx, let's say, so if we do something like d small x dy by d small x, that is exactly equal to d capital Y by d capital X. The reason being that x and capital X and small y and capital Y are related by constants, not something which is a variable, right? So in that case, it won't appear, and that's additive again. The most important part is this is additive. So the derivative will not change when we take the derivative of small y and capital Y. They're exactly the same. Particularly the reason is because the addition or the substitution is linear, right? So now we replace the values of small x and small y into the example that we have. So which means we can replace it with small a x plus b capital Y plus a small h plus b small k plus c upon capital A x plus capital B y plus capital A h plus capital B k plus capital C. So here we see that this particular values or this particular expressions that we have, they have taken some form, and now we will analyze what these forms can do. The constraint now on choosing small h and small k, as we discussed, is that choose h and k that we have used previously for the substitution in just a few steps ago, so that a small h plus b small k plus c is equal to 0, and capital AH plus capital B K plus capital C is equal to 0. Both these identities need to be satisfied, both these conditions need to be satisfied in order to use the substitution and to use the reduction to the homogeneous form, right? So let's take a moment and appreciate this fact. What really happens if we take this as 0? What really happens if we take this as 0? The expression above reduces greatly to a form which is much more easy to deal with, which is much more solvable. So let's say dy by dx is equal to small a capital X plus b capital Y divided by capital A capital X plus capital B capital Y, right? So we have completely gotten rid of small x and small y on the right hand side, right? Now, we need to do this problem in a way that we can solve it, right? So now we see that the way to solve this problem is solution strategy. Right? So let's take this example. Small a, capital A is equal to small b, capital B is equal to 1 upon m, right? And therefore, that's dy by dx is equal to ax plus by plus c upon small m ax plus by plus c, right? So this is the concept that we have. This is what we are looking for. But upon this constant, upon this condition that we have, so this is also called as a case of failure. This is also called as a case of failure. So we arrive at this expression where we have dy by dx is equal to this value, right? So how do we solve it now? So let's replace ax plus by is equal to z and use method of separation of variables, right? So once we get this idea of how to approach the problem, especially given the situation that we just arrived at, so this is the case of failure actually, okay? So we arrive at this expression, which I highlighted in the box, and then we have another solution strategy, but we need to be careful about this case of failure. The case of failure defines a situation where probably won't be able to, get past certain things, right? But this is a case of failure where you have small a upon capital A is equal to small b upon capital A, and that is a constant, that's a number, and then we replace it back into the form, and then we apply the separation of variables. So this is a special case, but we will see how to use one of the strategies for this problem and commence this lecture. So, right. Let's try to solve an example based on what we dealt so far. So, example. Okay, so solve dy upon dx is equal to x plus 2y minus 3 upon 2x plus y minus 3. All right, so that's a very familiar looking expression from the one that we saw, that we have seen, and this is very similar to the one that is mentioned over here. It's very similar to the one that is mentioned over here. So now we have this form which is given by this expression, right? So now we use the rules that we have said, which is put x is equal to capital X plus h, small y is capital Y plus k, h and k being constants. I'll try to solve this problem pretty quickly, but if you have any issues, feel free to comment down below or mention if you have any issues so far. Okay, so now if we replace back small x and small y into the equation above, we obtain d capital Y by d capital X And the idea behind d capital Y by d capital X instead of d small y by d small x has been mentioned previously. Just to reiterate on that, we use that because the substitution is linear, so we don't have to worry about the derivatives. Okay, linear substitution, that's the key word. Capital X plus H plus 2 capital Y plus K minus 3 upon 2 capital X plus H plus Y plus K minus 3, and that is equal to X plus 2Y plus H plus 2K minus 3. And that's very simple algebra. Essentially, we don't have much rocket science going on here. It's only the substitution part that really comes about as something a little difficult to work with initially, or to understand which one to substitute first. So HK is chosen so that H plus 2K, the two expressions that we have over here, these two must be 0 and at the same time. So H plus 2K minus 3 is 0 and 2H, oh sorry, I just forgot to change the color, but it's okay, you can understand. And then 2H plus K minus 3 is equal to 0. That implies H is equal to K is equal to 1, right? If you solve these equations, it's pretty trivial to understand. Also, you can replace it back into H and K and get a similar value, okay? Now let's put it back into the expression. So we have dy by dx is equal to capital X plus 2y and 2x plus y. As you see, small a by capital A is not equal to small b by capital B, so we won't have to take the case of failure. So this is not a case of failure. And when we have a case of failure, this is what we talk about. And this is a point where we have to be very careful. But for this problem, we don't have to worry, right? So now substitution of variables, substitution of capital Y is equal to V capital X, right? So now if we put back capital Y is equal to V capital X into this expression, we obtain, and I'm skipping some steps, but you can just do it from the beginning and it's very straightforward. This is the expression that we get, 2Vx upon 2x plus V capital X, and that is equal to 1 plus 2V upon 2 plus V, right? And then we do a similar technique and ultimately obtain at this form, which is 1 minus V square upon 2 plus V. And then we take the logarithm, which we did previously. It's a little complicated integration, but not so difficult. So let's just do it that way. D capital X by X is equal to 2 plus, and then we have on the numerator, of course, 2 plus V upon 1 minus V square, and then dV. So we do an integration, right? But then before we do the integration, we need to split this into a very smart technique so that we can do it, right? So this needs to be separated out so that we can do the problem a little bit easily. It won't be a pain to do it. So we can split this expression, we can split this form, and it's something to note about, split this form into two parts, which is 1 upon 2 1 plus V dV plus 3 upon 2 1 by 1 minus V dV. And if you add these two, it actually gets you to this value. This is like a smart substitution that we have done, and that is equal to dx upon x, right? So now we can do the integration, and again, this is not a definite integral, that is an indefinite integral. So we will face a constant, we will see that a constant appears, but that's okay, so long as we're doing it right, okay? So then we have 1 upon 2, 1 plus V dV plus integration 3 upon 2, 1 upon 1 minus V dV, right? So upon integration, we have this following form, and again, I encourage you to do this integrations all by yourself. These are very simple integrations, not very complex in a way that you have to face a lot of terms, a lot of expressions. No, this is not new, this is phi. All right, so that is equal to logarithmic of x plus log of c, and that's the constant. Finally, we arrive at this expression because we use some logarithmic identities, which is very easy to use. And we obtain 1 upon v by 1 minus v cube. And that is equal to c square x square, right? All right, but the game isn't over yet. We need to substitute back the expression of y. Substitute back y. So then once we have the expression over here, we will substitute back y, and we get an expression that looks like y upon x over 1 upon 1 minus x, y upon x whole cubed. That is equal to c square x square. And finally, when you reduce this expression, simplified, you can see that this is x plus y upon x, and there is an x cube in between, so that will sort of interfere a bit, but it's not very difficult. So x minus y, right, and it's whole cube at c square. Very easy, right? So finally, the final form of the equation is c square x minus y whole cube, right? But the game isn't over yet. Why isn't it over yet? It's because x and y are not the primary variables that we have. Our primary variables are small x and small y. So replacing capital X and capital Y back into small x and small y through h and k. Remember the h and k that we solved a long time ago, and we obtained the values of x and h and k from the simultaneous equation from the constraint conditions that we had. Now once we have this condition, what we will do is through h and k, once we have that, we replace it back. So put x is equal to small x minus 1, capital Y is y minus 1, finally giving back the form, which is x plus y minus 2 is equal to small a x minus y whole cubed. And that's the final answer. And a is essentially a constant that's reminiscent of c square. So you can write that as a or something else, but that's a constant. But this is the final solution. And as you can see, we did a lot of substitutions. Initially, we came up with the constraint conditions. We solved for h and k. And then what we did was we substituted the value. We did an integration, substituted it back, and then another substitution to get back to small x and small y. And that's the final form of the value. Right, so that's it for today. I hope you liked the video, and see you guys again very soon. Thanks.